Dramatic pause. Hope everybody's having a good Friday. Day before leap day. Very calm in here today. It's not very loud in here today.
Wonder why.
Wonder why.
Yeah, wonder why. Peter.
Shout out Cleveland. What's that?
He'll actually watch it.
He will.
I think he's
I hate you.
Yeah.
just now.
Yeah, I think you're right. I think he just sneezed. Marking one down.
An honorary sneeze.
Yeah.
Sees it all the time.
All right. So this is another section that we've done in every single one of our chapters so far. Now we're going to do curve fitting. Okay? What does that mean? That means we're going to get our calculators, put them in our lists, run our regressions. Now the nice thing about this, remember back in linear regressions, there was only like one option. It was just linear regression. In quadratic regression, there was just one option, quadratic regression. Then we got to polynomial, and it was like, okay, well now you have to run cubic and quartic and quadratic and see which one was the best value. Okay, for logarithmic and exponential models, there's only one option for exponential, and there's only one option for logarithmic. That's it, okay? And I have to be very clear about telling you which one's which. It'll be in the context and the directions of the problem. All right. So analyzing data values can identify a pattern or repeated relationship between two quantities. What a broad statement that is. We've looked at values, where we had, statistics where we've had a straight line pattern. And we've looked at statistics where we've had a parabolic pattern. But now, what happens if my statistics look like this? Right? That would be like an exponential model. Okay? Or what if our statistics look like this? That would be a logarithmic model. Right? So sometimes our data can make these shapes as well. That's the moral of the story here. Take a look at this table. We introduced this at the very beginning of the chapter. When you're looking at your y values, it's not differences, it's constant ratio, right? It's a constant multiple. What am I going from each y value to each y value? I'm multiplying 3 by each time, right? We talked about that whole doubling of a dollar thing, right? Remember way back when? That idea is I'm constantly multiplying by the exact same amount. This is 2 times 3 to the x. Sorry, misspoke. 2 times 3 to the x. Where if I look at my y values, I am multiplying by 3 each time. That 2 has no bearing on what I'm multiplying by each time, right? That just affects my y-intercept, where I start, and my starting values up front. So I'm multiplying by a constant amount each time. Thinking back to linear functions and even quadratic and cubic, we were looking at differences. Our first differences meant it was linear, it was constant. Our second difference, if it was constant, meant it was quadratic and cubic and quartic, so on. Now I'm looking at constant ratio. Notice that the ratio of each y value, blah, blah, blah. Let's take a look at it. All right. Can I find a constant ratio? Can I find a constant? How do I find what I multiply by each time? Think about this. If you're having a hard time saying, okay, what do I do? What do I multiply 2 by to get to 3? Can't you just make yourself a little equation? 2 times what is 3? 3 halves, right? 1.5. I'm going to multiply by 1.5. Same thing here. 3 times what is 5? Well, 5/3. What is 5/3? 1 and 1.6 repeating? Well, I'll make that a repeating symbol. Yeah. Now, I can stop right here because I know that this is not going to be exponential. Okay? Because those two values did not come out the same, I can stop right here. This is not going to be exponential. But what is the pattern? How do we figure out what the pattern is? Well, just like if I was to truly find the differences, I could take this one minus this one to get the difference of 1. I would be going up 1. I'm going to do this one divided by this one. 3 divided by 2. 5 divided by 3. 8 divided by 5. 12 divided by 8. that's going to tell you what your constant ratio is going to be, or if there is a constant ratio. Okay, so see if this is exponential.
Oh, look.
That's the bad part about it being so quiet.
Yeah.
We can hear
Ian was
everything.
here, you wouldn't even have heard it.
I know. This is both sides.
Gosh, dude, it's ghost town. Let's just raid this school. It's ours.
I thought there were sophomores in that class.
Yeah, they're all.
Oh my god, it is.
No, that was not fun.
Maybe at the end of the year. If we get done with that.
Dude, I hate that. I'm so mad.
Is this exponential?
Yeah.
Yeah.
Sure is.
Okay. If I take 24 divided by 16, I get 1.5. If I take 36 divided by 24, I get 1.5. If I take 54 divided by 36, 1.5. Yeah, we should check all of them. 81 divided by 54, 1.5. So I do see a constant ratio, so we would call this exponential. Okay? So if there's a constant ratio, it would be exponential. If there's not, then it's not. All right. Okay, let's get out our calculators. Find an exponential model for the data. Now, right there, right in that first sentence, it's telling me which model to use. There is only one type of exponential model. You'll see it in your calculator in a second. It's EXP reg, exponential regression. So let's do what we always do. Let's do this. Let's make so this is a table of tuition rates at University of Texas at Austin. Okay, so let's put in our data. Let's make this value, let's make our year end number the X value. Okay. I'm going to clear out my lists. Bless you. Should I add that to this?
That's two.
Uh-oh.
Oh, they come in more than Dude, weird, but like,
Okay. We doing all right so far? Okay, so now we would go and run our regression. So watch. Stat, calc, scroll down past all of our polynomial ones, and then EXP reg. Look at the one right above it. LN reg. That's going to be our only logarithmic regression, natural log regression. Okay, so those are 9 and 0 here are the only ones that we're going to be choosing in this section. But again, it has to tell you within the context. It'll say, use a logarithmic regression. Yeah.
What is power regression?
It's different. We won't learn about it.
No.
What is it? What do we get when I do it? Well, okay, never mind. I'll tell you when you're older.
Okay.
All right. CCP. Yeah, there you go. I've actually never used power regression, that's why. Okay, X reg. There we go. So look at what it's giving it to you as. A times b to the x. They're giving you a starting value and then a base raised to the x. So this equation is really quite simple. F of x is equal to A, 3235.64 times B, 1.07 raised to the x. That's our function. That's what models this data. Now, it asks me, use the model to predict when the tuition at UT Austin will be $6,000. Okay, so I want to put this into, and now how good of a fit do I have? Pretty good fit, right? So I go into my y equals, let's clear out what we've got there and turn on our stat plot. And now put our regression right in there. Yes? Something's wrong. Hold on a sec, let me put the function in here. Vars, statistics, EQ. Okay, and I'm gonna zoom stat.
Man, this thing is like the line is terrible. He's bad at his job.
I don't know, if you zoom out, it looks pretty nice.
Only crosses through one.
Well,
Zoom out
across pretty good.
I don't care.
Listen, if you took out that first point, it would be beautiful.
All right. So there's my scatter plot and my exponential regression. Now, I want to know when it's going to reach 6,000. So what is that? Is that an x value or a y value? That's a y value, right? So I'm going to go into y equals, and I'm going to say, okay, I want to know when my y value is going to be $6,000. Okay, now I'm going to zoom fit this so that I can see both lines coming across. Now, do I see my intersection point on here? Zoom out.
No way.
Oh, there he is. Yeah, did you happen to sneeze this morning? We felt like there was a sneeze during class.
Probably. There was a
Counts it,
sneeze.
counts it.
Yeah, I get
Why
it.
were you, did you have your
New shoe.
You're done?
Wow, that was fast.
Wait, what was the second
That's
one?
right.
What do you have to do?
Y equals 6,000.
Huh?
If you take out that first point, it's 0.99. Isn't that beautiful? Turn it on and off. Yeah, it actually works. I'm not. Every time I
Yeah. And then, did you put 6,000 in yet? Okay, so go back to y equals 2,000. And do
Every time you just have to turn it on and off. When, when there's the little spinning wheel on the corner, when it turns gray, it's saying that the calculator is usually it's yellow, right?
Yeah.
Sometimes it turns gray and just nothing happens. It's just frozen. So
Okay.
that's what you have to turn it off.
So, I think I lost some of you, so I'm just gonna go back. Let me put it back to normal, because I think a lot of you got lost on the what to do after you put in your 6,000, right? So we were here, we looked at that, we turned on our plot, we said zoom, stat, right? We're here. So we want to now put in our 6,000. We go into our y equals, we say, okay, 6,000. And at this point, we do zoom fit. Zoom fit will show both lines on the screen. But we need to see their intersection point, right? Here's our exponential coming across. And then there's our 6,000 line. I need to zoom out to see my intersection point. Zoom 3, enter. Here's my exponential, and here's my linear, and I want to calculate the intersection. Enter, enter, enter. Okay, so in 2009, we believe that the tuition cost would have gone above 6,000. All the way back to 2000. I wonder what it is right now. Wonder what? Let's figure it out. Based on this model.
Well, what's actually accurate?
Yeah, really. Somebody look this up. Somebody look up tuition at UT Austin. Let's second. Oh, whatever. Second, calculate value
Yeah, you can find it anywhere.
Where are we at?
In state, 10,610, out of state, 37,500.
Okay.
Whoa.
So we say, our model said 12,000.
Well,
And what is it?
In state, 10,000.
what was that, 2019?
What's out of state?
That was 1819. That's pretty good.
18.
That's pretty good. So what was it at 19? Second calculate value of 19. Whoa,
That's pretty good.
that's pretty good.
Everyone gangsta. So,
You know what's sad about this? We just did an exponential model to figure out what the tuition cost would be. Really? Wow, great. Fantastic. Way to go, UT Austin. Your tuition is going up exponentially. All right. Take a look at this one here. Now, look at the first line. Use a logarithmic regression. Yeah. That is going to tell you, okay, I want to use ln reg. The context of the problem will tell you which one to use. So what do we have here? It looks like we have a time versus speed. Like we ran something and we were looking at different time values in minutes and the speed versus time. Okay, so it looks like it's going up and leveling off, which is something like a logarithm. So I'm going to go into my calculator. I'm going to go stat edit, clear out everything that's there. I better check mine. I entered that really quickly. 2.5, 3.5, 4.5. Okay.
Well, that's pretty good.
Okay, stat, calc, ln reg. Oops.
Oh.
Yeah, triple nine right there.
That's good.
That's a close one.
That's a good one. That's. Wait,
You're so right.
Peter,
That
I don't
is
know.
one.
We make the appointment between first period. What is first period? That's hard to make up. I make an appointment for 7:30.
All right, so how good is this model?
It's excellent.
Very good,
Look
right?
how clean that is. What a
Yeah.
woman.
Okay, so now we go into, let's clear out everything that's there and go to vars, statistics, EQ, put our regression equation in, plots on, zoom. I'm going to zoom 6 before oh, look. I don't even need to zoom stat, do I?
You see a fire?
Yeah, zoom 6.
It's literally what we've done.
What?
I don't know.
He was looking over and like, what is he looking at?
So your first guess is fire.
Fire. It's a fire.
What do you see, boy? A
Dang
fire.
it, it's green again.
What?
All right, so here is my natural logarithm model, right? When will the speed reach 8 meters per second? So is 8 meters per second an x value or a y value?
Why?
It's a y value. So I need to go into my y equals and say, okay, when is the y value going to be 8? When is the y value going to be 8? Okay, I'm going to zoom. No, not zoom. Well, I wonder if I see it on my graph. No, I don't. Okay, I need to zoom out. Zoom 3, enter. Awesome. I see my intersection point there. Second calc, intersect. Oh, now I'm not getting anything. I'm trying to hit enter and I'm not getting anything. I need to go to the right 1 unit, right? Oh,
Oh, he didn't wait.
I hit it way too many. There it goes.
Oh,
Oh, there it goes.
Going.
Let's go.
What is it doing?
Oh,
Oh my gosh.
Very nice.
Okay, enter.
Yeah,
Okay, sorry. I hit it way too many times and it was like acting on its own. Okay, so at what time is it going to reach 8 meters per second? 16.6 minutes. 16.6 minutes. Right? And now I want to know what it's going to be like in 15 minutes. Is 15 an x value or y value? An x value. Second, calculate the value of 15. The speed is going to be 7.73 meters per second.
So is there a way to see what like the differences between the y values on that chart? Like,
Yeah.
as opposed to the multiplication or the small differences?
Let's go.
Wait, what do you mean?
Like with the, I forget what it was called, but the difference.
The common ratio?
Yeah. What was there? It's because with the exponential, it's
Hold on.
Department interruption. At this time, 8th grade students should report to the performance art
Oh, yeah.
hall to the musical. Students.
I wanna go.
Can I go? I wanna see Willy Wonka.
My sister is on
When do we have?
So what were you saying?
like with exponential, it was multiplying between each one, and with the other ones, it was like the.
See, we would have, there would be something, no.
Okay.
Because because the difference is the ratio is happening in the y values, you should see something in the x values.
Okay.
Okay. All right, yes. I don't know, it doesn't say.
Just finding it.
Find the speed as relates to time.
Wait, it's all letters.
Yeah, that's all it is, folks. That's all we got, that's everything.
Oh, that's good.
Yeah.
Oh,
We put the homework up on the board
Dang
here.
it, I was hoping we didn't have any.
Sorry.
Well,
No, we don't.
I took, I passed